Okay, so hello everyone, welcome. My name is Egor Suvorov, and today I would like to talk to you about floating point numbers. What works, what breaks, and why. So this talk focuses on binary floating point numbers. We get them in C++ like float and double. We'll talk a little bit about math behind them, a little bit about standard behind them, a little bit more about C++ implementations like compilers and standard libraries behind them. It is not the only way you can work with non-integers in C++. There are also decimal floating point numbers available in third-party libraries, and there is also a proposal to include them in standard C++. They might be more intuitive for some applications, so you might want to check them out. You might also like fixed point arithmetic that, again, might be more intuitive in some applications. You might want to check out arbitrary precision libraries if you need 5,000 bits of precision and not just 50. But I would advise against going to them right away unless you know what do you need that much precision for. And there is also interval arithmetic, which is a really nice thing. Again, check it out, not focus of today. Let's start with floating point types in C++. The standard guarantees that we have 3 standard floating point type in C++, float, which is subset of double, which is subset of long double, but it doesn't guarantee much above. So it also allows for extended floating point types. It is implementation defined. And for example, in GCC, we have double, which is 8 bytes, and long double, which is 10. But in Visual Studio, those are exactly the same type that takes 8 bytes. It's also implementation defined what these types actually do. So when you type A plus B, it's implementation defined what will happen. That's bad news. Good news is that compilers typically use whatever the hardware gives them. And that typically means IEEE 754 standard. Which is good news, and that's our today's focus. Another bad news is that even the compiler claims that it supports the standard in full, it doesn't mean that there weren't some artistic choices that might make following the standard a little bit harder. And at sometimes it even feels like undefined behavior. You write some code and it behaves a little bit differently from what you expect according to these standards. Or you write a code, it works on your machine, then you send it to your friend and it works completely differently. Or you build it with a new compiler and it works completely different. All of these are signs of UB, and unfortunately or fortunately, it's not what's happening in here. But let's start with something similar. As a reminder, here are what normal floating point numbers look like. You get a number, you turn it into a binary exponential form, then you make sure that it starts with 1 dot, then the remaining bits are called mantissa. You also have exponent, those are integers, and you can easily write them into memory. So depending on the type, we get 1 bit for a sign, we get some number of bits for exponent, and the rest goes to mantissa. I could also talk about range of these types, but I think it would be a little bit misleading, because range is largely determined by how much bits you have in exponent, and I think that precision, which is how much bits you have for mantissa, is much more important, and much more trouble stem from mantissa rather than exponent. Floating point is designed to work with small numbers and big numbers reasonably well, and they care about relative precision. So in this talk, we will be mostly focusing on double. So for example, if you take a look at difference between 1 and the next number that is representable in double, the difference is about 10 to minus 16. If you repeat the experiment with 1 billion, the relative error is about the same, 10 to minus 16. However, if you care about absolute precision, then you might have some issues. For example, there are 2 to 52 doubles between 1 and 2. As you go higher, between 2 and 4, there are 2 to 52 doubles again. So they are twice as sparse. Then again, 2 to 52 doubles between 4 and 8, etc., etc. If you go towards 0, the picture is reversed. You get 2 to 52 numbers between 0.5 and 1, etc. So the denser, the closer you get to 0. And if you care about absolute precision, for example, in your particular game, a block has size 1, then it means that if a player spawns somewhere far away from origin point, they might have some fun effects, and they will create a dedicated wiki page that lists all these fun effects that they may observe in your game because of this floating point stuff. Now let's zoom in at what happens around 0. Around 0, we have the smallest possible normal number, which is called double mean in C++. And to the right of it, we have lots of doubles, 2 to 52, and they're the densest they ever get for doubles. But on the left of double mean, we have this big red gap between 0 and double mean with absolutely no numbers. It's not the end of the world by itself, it's not criminal, but it might have some issues if you do calculations. For example, if you have 2 numbers that are small and close enough to double mean, like low and end on the slide, and you want to do some linear algebra with them, like maybe some linear approximations. When you subtract these 2 numbers, you might accidentally get 0, because their difference is smaller than double mean, and it gets rounded down to 0. So again, not the end of the world, but if you want to work with these numbers, that means you will then have to handle this division by 0 everywhere, which is not great. So what we have instead is we have gradual underflow or subnormal numbers, and we just add another group 2 to 52 numbers between 0 and double mean inside that gap, evenly sparsed. So now we have same group of numbers both on right and on the left of double mean with same distances between them. And that way we have a new invariant. If you have two different numbers and you subtract them, then you will get not 0, which is really nice. So these numbers are called subnormals. They are represented in slightly different way. They work slightly differently from normal numbers, and they solve this problem of accidental division by 0. Another special thing that we get in floating point numbers are infinities. Again, they are a little bit helpful for some cases, like overflows. When you want to check whether a times b is greater than c with integers, you have to handle some special cases, like whether b is equal to 0, what is the sign of b, so the division actually works. With floating point, you just write a times b greater than c, and if it overflows, then it becomes positive infinity or negative infinity, depending on the sign, and it works more or less as expected. Standard functions also work with them, like exponent of negative infinity is 0, and logarithm of 0 is negative infinity. Allegedly, that leads to simpler code, less branching, as you don't have this special case of b equals 0, and hopefully more utilization and better performance. Another thing that we have is sign 0. So by default, you get positive 0, which is plus 0 or just 0, as it's called in C++. If you negate it, you get negative 0, which is equal to 0. It's greater than all negative numbers, obviously. And the only thing where it matters is when you divide something by negative 0. For example, if you divide 1 by infinite, you get, 1 by positive 0, then you get positive infinite. If you divide 1 by negative 0, you get negative infinite. And that might be useful in some cases where you care about the sign of the resulting expression, but you don't really care about value of the resulting expression. So if you had an overflow somewhere in the middle, then you will get a reasonably correct result. At least you will have the same sign. Might be useful. And the last thing that we have is NaN, or not a number. It's actually not a single value. There are a whole group of them, and they typically appear when you do something that looks invalid from a mathematical point of view. Like you take a square root of negative number, or you take not a number and add number to it. That's also not a number. Or you multiply 0 by infinity, which doesn't make much sense in undergraduate calculus. But on the other hand, multiplying positive number by infinity makes sense in undergraduate calculus, so we get infinity instead of none. Again, might be helpful for some cases. We'll investigate NaNs a little bit more later in the talk. Now let's talk about rounding, because all of this is fun, but we don't have infinite number of doubles, and they will be rounded like on inputs, on outputs, during compilations, everywhere. So we need to understand how it's happening. There are multiple rounding strategies. We can truncate fractional part, and that means we're rounding towards 0. We can round towards negative infinity. That works differently for negative numbers. Or we can round to the nearest number, which is the default in IE 754. Note that I only round to integers. We will be talking about rounding to multiple decimal places later on in the talk. If we want to round to the nearest, then we also have to define a tie-breaking strategy. So what if our number ends in exactly 0.5? Tie-breaking strategies are similar to rounding strategies. We can round tie breaks towards 0. We can round them down. We can round them up. We can round them away from 0, which is what I was taught in primary school. So 0.5 goes up, 0.4 and everything else goes down. Or we can do what is called half to even or Menkel's rounding. And the idea is reasonably simple. So if tie breaking matters to you, that means you get a lot of ties in your inputs. You get a lot of numbers that end in exactly 0.5. And that probably means that you want to round half of them one way and half of them another. So hopefully all these errors in rounding cancel each other out, which is exactly what happens with Menkel's rounding. So I have an example here, 3 numbers, 0.5, 1.5, 2.5. Their real sum is 4.5. If I round them with Menkel's rounding and then add together, I get 4, which is the closest I could get. With all other strategies of tie breaking, I get either 3 or 6, which is slightly worse. Now, where does this actually happen? So first of all, it happens when you write your program and you compile it. So when you write 0.1 in C++, it's a mathematical abstraction. It's not a real number that exists in C++ or binary floating point arithmetics. In reality, it's rounded during compilation to the nearest possible number that is representable inside double. So whenever you try to prove or read anything about binary floating arithmetics, please make sure that when you see 0.1, you understand whether it's a mathematical abstraction or whether it's an approximation of number that is double or float. So by default, compiler will round to nearest representable, tie to even. We'll talk about even on the next slide a little bit. And note that it doesn't necessarily mean that you will get the same digit in the beginning. So 0.1 happens to be rounded upwards. So with infinite precision, it starts with 0.1, some zeros, some digits. But 0.3, when printed with infinite precision, starts as 0.29999, etc., etc. So there is also an interesting question, like what is the tie between the maximum possible double and infinity? Because if I type a very big number, it will become infinity, but at what point it gets rounded down to double max is separate questions that we won't touch today. What does it mean to round halves to even with compilers? Well, even just means last bit of mantissa is 0. We're working in binary, so even looks at last bit of mantissa, not as decimal representation. So I have here 3 numbers, A, B, and C. These are floats. They come one after another. And if I write these values in my C++ program, they will be represented exactly by the compiler. But if I write some numbers in between them, like x and y at the bottom of the slide, then the compiler have to understand whether x is actually closer to A or to B and choose appropriate value. In my case, x and y are equally distant from A and B, or from B and C in case of y. So the compiler has to, first, understand that this number is equidistant from A and B, and second, it has to understand that B is the one that has 0 as last bit of mantissa, so x is actually rounded to B, and y is also rounded to B. And compiler has to be smart, because if I change just one last digit of number y in my source code, so that 500 becomes 501, then the compiler has to realize that there is no longer a tie, and this big number y is now actually closer to C, even though it's not representable in float exactly. So it has to do something during compilation, and the same happens with doubles, with double literals. So fortunately, this is a solved problem, so compilers work. Compilers may be doing some arbitrary precision arithmetics inside. I'm not really sure, probably they don't. And yeah, you just need to know that this exists, it works reasonably well. Now, after compilation, we have runtime. So when we want to add 2 numbers together, let's say we want to add 0.1, which is really this number on the slide, with 0.2, which is really this number on the slide. What happens is the CPU will add them with infinite precision. They will get the next number on the slide, which is close to 0.3, but not exactly. And this number is unfortunately not exactly representable in double. So it have to round it. And again, by default, the mode is round to the nearest. And in our case, we have 2 options. One is slightly less than real 0.3, one is slightly larger than real 0.3. So we have to round to even bit. And in this case, it's the second option that has last bit of mantissa 0. So we get that 0.1 plus 0.2 is equal to 0.3, loss of zeros, 4, etc., etc. And this number is actually a bit further away from real mathematical 0.3 than the other options that we didn't choose. So now we have this classical example that happens in C++, Java, JavaScript, and most languages when 0.1 plus 0.2 is not equal to 0.3. So this is why it's happening, just a bunch of rounding. So we had all these rules, and now the question is, are these rules consistent between compilers and different machines? As you might guess, because I have a separate section for that, the answer is not really. We will start with GCC, and GCC has a separate web page that tells you how to report bugs, and it has a separate section that tells you which bugs are not really bugs, and they don't want you to report them. And one of the examples that they have is this one. We have number A, which is 0.5, which is exactly representable in double. Well, at least it should be. And then we have number B, which is equal to 0.01, which is not exactly representable to double, but according to standard rules, it should be rounded a little bit up. And then we just divide A by B, and we don't expect to get 50 exactly, but we expect to get some number, we truncate it to integer, and print. What will be the result? And then we do the same thing, but we divide in a separate lambda function. So in the first line, we might get 49 because the real result with infinite precision here is a number that is slightly smaller than 50 because 0.01 is actually slightly larger. Or we might get lucky with rounding and get 50 exactly. In that case, it will be truncated to 50 instead of 49. So we expect either 49 or 50 in the first line, and I personally would expect the same result in the second line. As you might guess, both assumptions are wrong. If I try GCC and I compile it in 32 bits with C++ standard, then I get 49 in the first line and 50 in the second line. What's even more surprising is that C++ is supposed to be the most pedantic version of C++ that GCC supports, and GNU++ 20 is supposed to be relaxed C++ with some GCC extensions. So if I remember correctly, this worked the other way around a year ago, so I think they fixed something, but maybe I just misremember. Visual Studio and Clang print 50/50 in my tests all the time. So what's really annoying about this is not that GCC disagrees with other compilers, is that a simple refactoring like extracting an expression into a function might change what you see. I believe the same thing can happen if you add a debug print. So yeah, that's not great. That really feels like undefined behavior. Not cool. So I believe it's not undefined behavior. So what is happening here? And what is happening is called excess precision. So when you divide 0.5 by 0.01 and all those extra numbers with infinite precision, you get this number on the screen. I highlighted mantissa with yellow, and the next bit after mantissa is in red. So we get this number as a result. It's not exactly representable in double, so we have to round it, and we have the options where to round it. We either round it up to number 50 with all bits zeros, or we round it down to the previous representable number, which is 49.9999, etc. And then the next bit after mantissa is 0. So with 52 mantissa bits, 50 is closer. So if our calculations are completely within double, we should get 50 exactly. And that's what Visual Studio and Clang do. If we increase the number of mantissa bits from 52 to 53, we still need to round it up because the next bit after mantissa is 1. And if we have at least 54 mantissa bits, then the next bit is actually 0. So now we are rounding down to 49.9999. And yeah, so actually that's more or less the explanation. When you work with 64-bit GCC, it uses SSE instructions and 64-bit registers, same as double, so we always calculate everything in double. But in 32-bit mode, GCC sometimes uses 80-bit register from x87 from last century. And it thinks, well, I've already divided A by B in this 80-bit register. I will then need to truncate it to an integer. So there is actually no need to truncate it to 64-bit double after each operation. I will just throw in a little more precision for free for the user, because extra precision is fine. Well, apparently it's not always fine because it changes what decision we make within our program, which is not great. It's an old issue. It was first reported 25 years ago. I'm not sure if it was still about excess precision back then. Maybe it was something different. It's like an umbrella issue. I first encountered it 15 years ago when I was doing some competitive programming. I discovered it the hard way because my solution failed during system tests while it worked for me locally, which was a bit annoying. And a game developer found it a few years ago when he wrote this nice blog post how he joined the bug research community. I believe GCC added some switch to C to fix that, and they also added it to C++ maybe a year ago. It didn't work for me for some reason, but yeah, I'm not sure. Maybe I'm not trying hard enough. This is not the only issue with reproducibility we have. There was actually a nice talk by Sherry Ignachenko last year at CppCon. We may also have some bad optimization. For example, in floating point numbers, we can set a rounding mode during runtime. If we don't want round to nearest, we can round toward plus infinity or negative infinity. And compiler might sometimes break it if they want to rearrange negation signs around. This can be disabled with a separate GCC flag. Or you might want to compile it with fast math mode, which allows compiler to do more incorrect optimizations. By incorrect, I mean that they are not correct in presence of roundings as we do with floating point arithmetic. They are mathematically correct, but they are not correct in IEEE 754. We also get excess precision, and we also get a case of excess precision that is called fuse multiply add. Some CPUs support a separate instruction that allows you to do multiplication and addition in a single step. And it is faster. It sometimes allows you better precision, which might or might not be what you want. So it's a case of excess precision. So it becomes harder to understand what your code will actually do with all these numbers. if you have all of this in a modern compiler, and you do have this in a modern compiler. So if you, for example, try to implement a Hahn summation algorithm, which is mathematically equivalent to just calculating sum of all numbers, but it does it in a slightly clever way, so all these errors are accumulated in a separate variable, and just providing better precision. Well, you can't really be sure that this algorithm works as intended when you use a modern compiler. You have to actually inspect the assembly code. OK, so do we actually get any guarantees from any standards? As a matter of fact, we do. So we know for a fact that 4 standard arithmetic operations and square root are calculated exactly to the last bit. At least that's mandated by the standard, and that's what happened in my naive tests. For some functions, for all other functions, we don't have that guarantees. For some, we now have, as a matter of fact. For example, for sin of a very large number, we don't know how to calculate the twice, at least I don't know. It is a solved problem, and actually most standard libraries do calculate sin exactly to the last digit. I'm not sure if that's meaningful, because if you fluctuate input of sin on such big magnitude a little bit, then output changes significantly. So not sure if it's even useful. But the really bad thing happens with power function. For all I know, some standard libraries might implement it with exponentials and logarithms. And 10 years ago, again, during competitive programming, someone discovered the hard way is that if you try to square number 10, then you not always get 100 exactly, which isn't great, because inputs are precise. The output can be precisely represented in double, but it's just the function itself that is not ideal, and it's actually permitted by the standard. So I decided to check whether this still holds. So I wrote this piece of code. I go through all numbers between 0 and 100, and I only check those that have a to the power of b less than, let's say, a billion of a billion, so I can double check it with long longs later on. And then I run it across several machines in different compilation modes. So what I got is about 1% of incorrectness. So you will not find it like during your day-to-day work, probably. You might find it accidentally. For example, with 32-bit Visual Studio, if you raise 7 to the power of 19, you get an incorrect result with the embedded POV function, but I think it doesn't happen with GCC when you compile with libstdtc++. And also, this set of incorrect inputs is different for bitness, for different compilers. So yeah, that's like one more thing to be aware of. POV is not guaranteed. If you need POV of 2 integers, just write it yourself, I would say. OK, so now we have a lot of things to care about. How do we debug issues when they happen? We need to print numbers. Turns out it's also not as easy. If you print it in default mode with cout, what you get is %G specifier for printf, which prints 6 significant digits and not more. It rounds everything to 6 significant digits, even if you have an integer that has more significant digits. And then it also sometimes switches to scientific notations to try to make the output as short as possible. So for example, if you were to print 0.1 plus 0.2, it will print 0.3, even though 0.3 is not what we really have here. We need more significant digits. How much more? Well, there is a nice constant called max digits 10, which is exactly what you need. For float type specifically, it is 9. That means that if you print 9 significant digits in decimal, it's always enough to uniquely identify float. 8 digits might be enough sometimes, but not always. For example, on the slide, I have 2 numbers that end in 0.156 and 0.164. These are 2 different floats, but if I print them with 8 significant digits instead of 9, they are both rounded to 0.16, so they are glued together. This is not an obvious fact, because we only have 32 bits in mantissa in float, and that means about 8 million values, so I would expect 7 digits, maybe 8, but no, turns out we need full 9 decimal digits to print this. So yeah, please use this constant instead of trying to calculate it yourself. So the mnemonic here is if you're looking for some number that specifies the minimum possible digits you need to uniquely identify something, max digits 10 is your friend. Don't confuse it with another constant that is called very similarly. It's called digits 10, and it is actually equal to 6 for floats. And it tells you about conversion the other way. How many decimal digits can you store in a float precisely and then get back? So it turns out you can always store 6 digits in a float precisely and then get it back, but it's not always true for 7 digits. Again, an example on the slide, I have this number 858,997, and then if I write 3 or 4, they both get rounded to the same floating point number when I store them. They get both rounded to 3. which is not great. And again, this example is not easy to come by because I looked through 10-digit integers and I found only that 0.3 of them are failing this test, and 7 digits are almost always enough. And for 11 and 12-digit integers, I didn't find any examples that actually don't store 7 integers exactly. So digits 10 is the upper bound if you're thinking like, what is the maximum number of digits that I can safely store? Digits 10 is different. So what is the best way to print? You can obviously print like 17 digits for double and 9 print for float, but the best way is to use std format from C+20, and it will smartly understand what is the minimal representation of a number that you have. So if you give it 0.3 rounded to the nearest representable double, it will understand that printing just 0.3 is enough. If you give it the result of 0.1 plus 0.2, it will understand that printing 0.3 is not enough, and it will keep printing more and more digits until we can uniquely identify that specific double and differentiate it from 0.3. In this case, it has to print all 17 significant digits. That is the max digit stand for double. So that's for numbers.
Green.
We lost the We're having some technical difficulties trying to fix that.
Yeah. I hope it's not about floating point numbers. We only have 2 screens here.
Does FMT
Yeah.
format do the same thing?
FMT format, not sure. I suspect it should do the same thing because they were like modeled one after another in a sense, but I haven't checked. Yeah, any other questions while we're waiting for screens?
Is there an interaction between like max digits 10, whether you're printing it in scientific notation or?
No, max digits 10s don't care about scientific notation. Scientific notation is merely about whether you print lots of zeros at the end or whether you print like e plus 9. So it's the same. There might be some like difficulties with specifying number of digits because there is like plus minus 1 errors in printf modifiers, I believe. So sometimes they account for like sign in the beginning, sometimes they don't. So that might matter, but not much more.
Should I bother knowing about posits?
Second?
Should I bother knowing about posits? As an alternative to 754?
Worrying about, I'm not sure if I can hear you.
If I need to bother about posits, which are a different representation of floating point numbers other than 754.
Yeah. So yeah, the question was, should we care about other representations for floating numbers other than 754? I don't, and I live. So I've heard that it was a real issue like 40 years ago when the standard was invented, and there was some situations with some formats where you can say, for example, you had like a divided by like a plus 1 greater than 1, or it's like some weird stuff like this. It's not happening in 754. I suspect there might still be some hardware around that doesn't support 754, or maybe there might be some bugs in emulation. But yeah, I'm not aware of any hardware. So yeah, if anyone has experience with non-754 in the last 15 years, please speak up. Should I try maybe disconnecting laptop?
You could try it.
Yeah.
Are these ways of handling floats a carryover from C or choices that C++ made?
Oh, yes. There are some things that we carry from C and C++, specifically std complex type, which I will be talking in a little bit if the slides fix. But yeah, and it actually means that sometimes C++ is not as optimal because it has to keep compatibility with C. I'm not sure if it's intentional or if it can be fixed, but yeah, that is an issue. I also heard that C might have some slightly different choice from C++, but my understanding is that neither standard really talks about floating point numbers. They just refer to 754 or just say it's implementation defined stuff.
Are there cases where you think people should consider using decimal floats?
Yeah, for sure. Yeah, the question is whether there are cases where people should use decimal floating points. Yes, for sure. For example, if you're working with real people, then real people typically think in decimals. So they type in some numbers like 1 to 0.5 plus 3.5, and they expect the result to be exact, which will be the case for floating point numbers sometimes, but not always. And when it breaks, it's extremely hard to get rid out of your system, because if you're already using binary floating points throughout your system, It's already there. It's like stored in binary. It's stored in logs. It's in all APIs. So you can't really switch to decimals. But yeah, so like if you're designing some financial application or something that you will give financial people to work with, so yeah, please use decimal floating point numbers. The downside is they're not as popular, so there might be bugs. They might have significantly degraded performance because they're not supported by modern hardware, I believe, but I might be mistaken. So yeah, for sure, like for example, Excel, I think, uses 754. Well, part of it, for example, Excel doesn't support denormalized numbers because they behave weirdly, and not sure if I fully agree, but I can see some reason behind that decision for Excel. And yeah, if you're working with financials in Excel, you may accidentally get all this fun stuff and rounding errors and lose a cent or maybe $1 or maybe more. And it gets even worse if you are doing something that is mandated by law. Well, if your auditors also use Excel, you might be fine, but otherwise, not so sure. Next slide is slide 36. So we were talking about how we can print numbers. What about non-numbers? What about infinities and NaNs? Well, the situation is reasonably simple. Everything is case insensitive. We have two different spellings for infinity, inf and infinity. For NaN, we can also have sign of NaN because sign of NaN is part of its payload. And we can also have implementation defined information in parentheses after NaN, optionally. So my GCC is chill. It just prints inf, NaN, negative NaN without any information. But Visual Studio actually uses this heavily. And it can have quiet NaN. It can have signaling NaN. It can have indefinite NaN. All of them are spelled differently. Before Visual Studio 2025, we also had a completely different spelling just for Visual Studio. But I believe now it's standardized in C++ and Visual Studio agrees. Again, it's not the end of the world if you have different spellings for NaN, like sign, maybe something after the NaN, but it gets worse if you want reproducibility across platforms. For example, if I take this line of code, which is cout square root of -1, and that's the line. So if I build this line with 32-bit Visual Studio for 32-bit Intel CPU and run it on my computer, I get as an output -NaN parenthesis int. So I get like 7 characters. But if I run the same executable on Windows ARM on my colleagues macOS with Parallels, I get just NaN. I get 3 symbols instead. And I believe that's because my Intel CPU and my colleagues' Mac CPU use different NaN payload for square root of negative numbers. And Visual Studio library stays the same, and it only handles NaNs that it expects on Intel CPU. And whatever it gets on Mac, it will just print it as NaN. So if you depend on that, well, yeah, here is another thing. The same application without any recompilation can work differently on different platforms. I guess because Windows ARM doesn't bother to change internal representation of NaN for some functions, which I can totally understand. Now that we talked about NaN, let's see about a few more things about NaN. So I'm now in section NaNs are special. First thing that you need to know about NaNs is that they are not equal to any number, they are not greater than any number, and they are not less than any number, which makes sense from mathematical point of view, but it also is not equal to itself. So NaN is never equal to none, which makes no sense from a mathematical point of view. And it also breaks lots of natural assumptions about how comparisons work, which isn't great. And I believe the initial idea behind the decision was that when the standard was first adopted last century, I wasn't there for sure, then they didn't have isNaN function in standard library of any language, but they still needed to provide some way of testing whether value is none. So they decided, okay, let's just assume that x is not equal for x is true for NaNs and false for all other numbers, which again, not a decision that might be the best, but I can see where they come from. And in practice, what does it mean? That if you have, let's say, an array of doubles that has none, then you can't sort this array without invoking undefined behavior. Because none is not equal to itself, none is not less and is not greater than any other number. So what happens in practice on my machine is that none just splits the array in all elements before none and all elements after none, and it sorts them independently. Of course, it's undefined behavior, so that's what's happening on my machine with my specific standard library, but it can just as well crash, it may freeze, it might time out, it may loop indefinitely, it may format my hard drive or SSD, because, well, we're in 2025 now. And it's true for sort, it's true for set, it's true for any in-house algorithms that you can write. So there is no way you can write a reasonable sort of doubles if you don't handle none in some special way. Turns out that IE standard actually has total order predicate that gives some order to nonce, positive 0, negative 0, and infinities. But I think it's not implemented in C++, and comparison of nonce is still implementation defined, so I'm not really sure whether it's useful. The next thing about nonce is their payload. So NaN has 1 signed bit and 52 mantissa bits that we are completely free to put anything in them except for all zeros in the mantissa. The initial payload is not specified. So again, square root of negative number on x86 CPU is negative sign. All bits of mantissa are 0 except for 1. And on ARM64 that I checked at Compiler Explorer, I get the same exact NaN, but the sign is now positive. I think it's implementation defined what we actually get. So it may depend on the compiler, on your compilation flags, on the underlying CPU. I believe the historical idea behind having these mantissa bits is that CPU might store some debug information inside NaN about the origin of this NaN, for example, address of an instruction where that NaN first appeared. So when you see NaN as an output of your program, you could then trace it back. I don't think of any system that does it currently. There are also notions of quiet NaN and signaling NaN that were also, I believe, coined for some debugging. So please share if you use them or if you use them in the last 15 years and it actually helped you, because I haven't found any non-theoretical applications for them. Another fun part that we can have with nonce is that we can notice that 52 is greater than 48, and 48 is the number of bits we need for a 64-bit pointer at the moment. So we can actually store pointers or even full strings inside nonce, and this is what some third-party libraries do. For example, in Bloomberg, we have this BDLD datum type that uses exactly that. And we do still have some guarantees about payloads in nonce. For example, if I have NaN1 with payload and NaN2 with a different payload, then if I make some operation with this nonce, it's guaranteed that I will get either of these nonce as a result. So if I add them together, then it's guaranteed that the resulting NaN will have a payload either of NaN1 or NaN2. If I take square root of NaN, I get the original NaN back. And there is also this std NaN function in standard library, and its implementation defines what it does with its argument. Visual Studio just ignores this argument completely, and GCC takes this argument, parses it as a decimal number, and then puts it into as a payload into NaN. There are also some fun corner cases where passing NaN as an input for an operation does not result in a NaN. For example, if we want to calculate hypotenuse of a right triangle with one side being infinite, then it doesn't matter what the other side is. The result is always infinite. And the standard decided, well, let's allow it for nans as well. So the correct implementation of the hypot function will handle NaN and infinities separately, and it might mean that it actually might be a little bit slower than your own square root of x squared plus y squared implementation. Not sure whether you really want to use naive implementation all the time. Maybe you need this behavior of hypot function, but on the other hand, it's probably faster than what the standard library gives you. I don't know, you have to benchmark. So we talked about all the stuff that makes floating point weird from programmer standpoint. Now let's talk about some math caveats that are not C++ specific or not GCC specific or not Visual Studio specific. One of them is even if we use simple operations like addition and multiplication and division, they are guaranteed to have the best precision possible. We still might lose some precision. For example, let's say I have coefficients A, B, and C, which are just like big random numbers and doubles that I have. And I want to calculate weighted average of 3 numbers using A, B, and C as weights. And let's say I want to test it, and let's say I want to calculate weighted average of numbers 2, 2, and 2. And I expect it to be 2, no matter what weights are, even as big as random as these ones. And I get 2 on my machine, which is great. But then if I try the same test with numbers 3, 3, and 3, I don't get 3 as a result. I get a number that is slightly lower than 3. And factor ends in like 99996. So if at any point I had an assertion that my weighted average algorithm works by plugging in equal values and checking that the result is the same, it won't work with all weights. So there is no really way to fix this in floating point arithmetic because it is inherently imprecise in some situations. Like this one. So the naive approach here would be to assume that closed numbers are equal. It's advertised all over the internet, and they say, well, floating point numbers are not precise, so whenever you compare numbers, always use it with an epsilon. And then some will go as far as to say, use double epsilon. It's the best epsilon you can have. It's in the standard. I would say that this recommendation might have some merit. So yeah, we can't really do better than to assume that if numbers are close, then they're the same, just different because of rounding issues. But using double epsilon is not really great. For example, it doesn't work for this example on the previous slide. double epsilon has some value. It has some meaning in the standard, but it's not one size fits all epsilons for all applications. So you should more or less eyeball what epsilon is good for your application. There might be some algorithms to figure it out, but again, I haven't heard of a person who actually sat down and decided that this is epsilon for my application. Here is like a robust proof. So people more or less eyeball it, I think. At least I haven't heard of a better explanation. And then you have to rewrite some operations within your program, like when you compare two numbers, you should instead subtract them and check that the difference is less than epsilon. When you check whether A is less than or equals than B, then you should also include those numbers that are equal to B. When you check whether A is strictly less than B, then you should exclude numbers that are equal to B. And it actually doesn't matter whether you use strict comparison or non-strict comparison, because if you have A that is equal to B plus epsilon, then your epsilon is wrong. Some rounding works, some rounding doesn't. Square root is a fun example because it makes some decisions around 0. So if your number is positive, it's OK. But if your number is equal to 0 when compared with epsilon, that is, it might be slightly smaller than 0, then real square root will just give you none, which is obviously what it does. So if you want to incorporate this like epsilon arithmetics into your program, you should take maximum of x and 0 and then give it a square root. Where you don't need epsilons is when you want to sort doubles or put them into a set. Standard comparison will work just fine, except for NaNs. And and you actually shouldn't put epsilon comparison in here, because then you might actually break some transitivity properties or other properties of comparison. That is, of course, assuming that you don't get bit by excess precision, which is exactly what happened to that poor fellow from a game development company a few years ago when he joined the bug 323 community. So he had a set of doubles, he had some custom comparator, and then he got some excess precisions and everything break. What you also want to do is you want to avoid some unstable functions. For example, if you want to calculate a polar angle of a point, do not go with arccosinus, go with a10(2), which is a function dedicated to calculating polar angle. Don't use POW function, just multiply a number by itself. Don't divide by first calculating 1 over b and then multiplying a by z. Just divide a by b directly. Don't use Heron's formula for triangle area. Just use vector product as a bonus point. It will also work for integers. And there is also a link about other things you might not want to do with, I guess it's a way in this direction. And there is a nice link that tells you about other things that you might want to do. OK, next massive thing that I would like to talk about is rounding to decimal places. So we talked about rounding to integers and tie-breaking logic. What if we want to round to 2 decimal places after decimal dot? Well, we need to decide whether we care about ties. If we don't care about ties, then we can just skip the next few slides. If we do care about ties, for example, in a banking industry, when you're generating a report and you have lots of inputs that are ending in exactly 0.5, then you do care about ties and you need to somehow handle them. So the naive approach would be to just use STT format or printf or cout and print with 2 decimals after the dot. But the trouble is that inputs are not precise. So if you, let's say, print 2 decimal numbers after the dot, and you print number 1.115, then it's not actually number 1.115 that is printed. It's actually rounded to the nearest representable double, which is actually slightly smaller. So it's actually rounded down. And if you try a different number, for example, 1.135, then again, it's not exactly 1.135. So the tie-breaking rule does not apply. It's actually a number that is slightly bigger. So it's actually rounded up. And that might result in surprising situation where if we print like lots of numbers, then we get numbers 1.12 as a rounding, as result of rounding. Then we get number 1.14 immediately without ever getting 1.13. So if you look at just some examples, then you might assume that you understand how rounding works, but it's actually you're just getting lucky. And OK, something happened. OK, cool. Yeah. So you might get some unexpected results if you assume that printing with format or cout will correctly round to two places after the decimal point. And that's because our inputs are not precise. So what you might want to do is you might say, well, we know that inputs are not precise in this case, but what if I multiply everything by 100? and then I round to an integer, because that way my inputs should be precisely representable. For example, if I multiply 1.115 by 100, I should get 111.5, which is exactly representable in double. And then all the standard logic of round and tie breaking should kick in. Well, it fixes examples on this slide, which is, by the way, slide 48, rounding to decimal places. But on the next slide, I have a different set of examples, a different set of numbers, and it doesn't work for them. So I've actually checked, and if I look at all 100 numbers between 0 and 2 that start with 2 digits and end with 5, then all of them except 7 get correctly rounded up, and 7 of them get rounded down, because when I multiply them by 100, I still get imprecise result. Because the input was so imprecise, multiplying it by 100 didn't fix that imprecision. So, which is not great, because you can write this incorrect code, you can check it for some random inputs, be happy that it works, but it actually doesn't work for 7% of the cases. And then even worse, you might not try it with 2 decimal digits, you might try it with 3 decimal digits instead, and it will work all the time between 1 and 2. So these examples, again, are hard to come by, and I had to specifically look for this one. Now, what is the correct solution? The correct solution is to do everything in integers. So you should know how many digits you had initially before you can round it correctly. So you should know that you initially had 3 digits. So when you multiply by 1,000, you get a long, you do some math here, and then you can divide it by 1,000 and print with two decimals after the dot. Of course, there are some corner cases here, like what if it overflows? Are there even enough digits in a double to print this a long after dividing it by 1,000, or should we print it separately as integers? But yeah, that's a separate question. Okay, so that was it about math. Now let's talk about some C+ caveats. C+ specific, it's not about floating points, it's just about plain old C++. My favorite example is this one. I have an array of doubles, and I want to print only those doubles whose absolute value is at least 0.1. And I use abs function for that. And with Visual Studio, I get all numbers as expected, starting with negative 0.5. But GCC and Clang only print all other numbers. They don't print negative 0.5. They don't think it's greater than 0.1 for some reason. And the reason is that I've included CMath header. And what actually happened is that I got abs for integers in the global namespace, and I got abs for floats in doubles in the std namespace. So when I said abs, I actually called the one for integers. So it rounded negative 0.5 to 0, took absolute value, which is 0, which is not greater than 0.1. And this actually happened differently on Visual Studio and GCC. So I assume it's actually a matter of standard library, not the compiler itself. There are 3 solutions to this problem. First solution is, of course, to use the appropriate std : abs when you include CMath. And the other solution is to include math.h and use abs from C-style times. So you will get both abs for integers and abs for floats and doubles in the same global namespace. And the third solution, which is my favorite, is to use fabs function, which doesn't exist for integers. It always exists for floats and doubles, or if it compiles, even if you call it from an incorrect namespace, it will work for floats or doubles as you would expect. So this is my recommendation. The next fun part of C++ that we have is float to integer conversion. So when you have a floating point number and you truncate it to integer, it will just drop the fractional part as it should, and then it will try to fit the result into an integer. If it fits, it's all good. If it doesn't fit, it's undefined behavior. It's not even implementation-defined behavior, it's straight away undefined behavior. So again, it can crash, it can freeze, it can format your hard drive. But what happens in practice, at least on my machine, is that GCC 14 gives me max int, GCC 15 gives me min int, and Visual Studio gives me some random set of digits. After some playing around, I believe that it's just my numbers that got truncated, truncated into long, and then long got truncated into 4 bytes of an integer. And I have no idea what Clang gives me. It just gives me some digits, but I wasn't able to make any sense of them. With integer to float conversion, the situation is a little bit better because integers fit into floats better than floats fit into integers. So if the result can be represented in double exactly, it will be. But if it cannot be represented exactly, for example, because we are taking a very big long, and there are 63 bits in long opposed to 52 mantissa bits in double. So if our long is very big and cannot be represented in double exactly, then it is implementation defined how it will be rounded. So it can be rounded down, it can be rounded up, and we have no control over it, and we don't know. So GCC and Visual Studio say in their documentation that they will round to the nearest, but they don't say anything about tie breaks, so not sure if that's of any help. And Clang just plainly doesn't say what their implementation-defined choice of rounding integers to float is. So yeah, be careful with that as well. Another fun thing that is not C++ specific, it's actually more CPU specific, is that subnormal numbers can be significantly slower. So I have a benchmark on my slides that takes a small number that is still a normal number, and it divides by like 1.1, which is another normal number. And this benchmark takes like 2 nanoseconds on some like random VMs that I had lying around. Then I keep the same code, but I divide by a subnormal number instead, and that benchmark becomes 25 times slower. I tried to reproduce it on my machine, it didn't. So maybe something is wrong with the benchmark, maybe something wrong with the virtual machine I was testing it on. Maybe I accidentally forgot some compile switch. That's possible, but I'm not the only one who noticed this. This issue. For example, MATLAB documentation explicitly tells you that if you use subnormal numbers, then you might expect about 5 times slowdown during your compilations, during computation, up to 50 times slowdown, which isn't great. And actually, some security researchers also exploited this thing, and they wrote some JavaScript code that loads, let's say, your banking account in a separate iframe, and by default, browsers shouldn't have access to that information directly, at least not from a third-party website, but they time how long it takes to render that page. They apply some CSS filters, and yeah, they were able to extract like 1,000 pixels a second, using the fact that subnormals are so much slower. So the alternatives is to use flush to 0, which basically says if you get subnormal number as a result of operation, flush it to 0. And another flag that is denormals are 0, which works for input. So if an operation sees the normalized number as an input, it just assumes it's 0. You can opt in into this behavior for some compilers, for some CPUs and GPUs. I believe it might be the default on some architectures even, but I'm not really sure here. So it will make your program faster, but on the other hand, if your program depends on subnormals that much that disabling them is a significant speed up, the question is, why do you have so many subnormals in your application? Like, is it normal for your application? For some applications, it is. For others, it's a sign of an issue. And the final thing that I want to talk about in terms of C++ issues is complex numbers. So in C99, we have complex type. In C++, we have std complex that should be compatible with C99. And it turns out it can be 50% slower than your own handwritten implementation of, yeah, thank you. OK, now we have 3 screens. So yeah, you can choose, hopefully. Yeah, so as I was saying, we have std complex in C++, and I have this benchmark here, and I had also my own version of complex numbers for flows written, and it turned out to be 50% faster with Clang on maximal optimization level. And it's not because standard library is stupid, it's because it's actually more careful than I am. So I just use the standard formula you learn in high school for multiplying complex numbers, but in standard library, they also define what infinite complex number is, what not a number complex number is, and all the separations have to handle this carefully. So they do it, but I believe they spend a little bit more CPU cycles doing that. And another fun thing that might happen is that std complex might actually be an alias for C type that calls actual functions with call assembly instruction instead of inlining them. And that means slowdown may be as large as 300%. So I ran it on Quickbench. I tried reproducing it on my local machine, and I got like 30% difference, not 300% difference. I also ran it on a random VM, and the standard library was actually 5% faster. So I'm not sure what's going on. Maybe my benchmark was wrong, but you're free to try it on your own. So yeah, if you use complex numbers, you might want to write your own if you don't care about NaNs, if you don't care about infinities, and you don't care about all these like intricacies of complex numbers. So yeah, we are getting a little bit closer to our time. Do I have like maybe 10 more minutes due to the technical issues, or are we running low on time? Ah?
I just said yes to be out of 15.
Okay, yeah. Okay, so to 3:15. Yeah, okay. Cool. Sorry, everyone. Yeah. Yeah. So now let's take a look at small examples that combines all of the previous presentation. Suppose we have a list that contains a mixture of long and doubles. For some reason, maybe we download it from Excel and we want to sort it. So we call std sort, we pass it our custom comparator that calls templated operator, and it then gets A that is independently long or double, and B that is independently long or double. And then it just uses a standard comparison to compare them. So if I run it on my machine, it works as expected. But if I run it with a different set of data, then it fails horrendously. For example, if I use these numbers, then V1 is equal to V2. V2 is equal to V3 according to my comparator, and V1 is strictly greater to V3, which you can actually see on the screen. And of course, that's undefined behavior. Anything can happen. SVG sort can break, yada, yada. But the question is, why is our comparator so broken? The answer is simple. C++ doesn't have operator for comparing long, and doubles. So when we ask it to do so, it just converts long into a double, possibly losing some precision, and then compares to doubles. Which is not great, because several longs can get truncated into the same double. So they compare equal, which is exactly what happened in my example. So the fix is to have two cases, one for small doubles and one for big doubles. So if you have a small double, so that there are actually more doubles than longs, so there are some doubles between integers, then we can convert our long to double. And yeah, even if we're losing precision, we don't really care. And the other case, if our double is so big that there are gaps and not all integers are representable in double, we can go the other way. We convert our double to long and convert to longs. So that's the main idea, and as you can guess by space left there are some corner cases to handle. So first of all, the behavior is undefined if our double doesn't fit into long. If it's NaN or if it's infinity, then it's undefined behavior. So we need to handle that. If A is not within long range, then we return. This doesn't work, but it doesn't work for a different reason. It doesn't work because L long max is actually implicitly casted to double. L long max cannot be represented inside a double precisely, so it's rounded either up or down, implementation defined. And if it's rounded up, then we get incorrect comparison. Then if A is actually L long max -1 or actually L long max exactly, then the check doesn't work. So what we should actually do is we should never compare doubles with some numbers that are not exactly doubles. So I can compare A with L long max +1 instead and use greater or equal comparison. And in that case, this code almost works. There are only a few things left to do. I can replace these long numbers with hexadecimals. It looks a bit nicer. And I can also handle NaN, which I should have done a long time ago. And now this works. You can also tweak it a little bit, but that's the correct way to compare longs and doubles. And yeah, so it's not as easy as it could have been. Now, in conclusion, when you work with floating point numbers, when you choose to do so, first of all, you should know your inputs. If you have this number as an input, is it this exact number that just happens to be slightly bigger than 1 to 3.65? Or is it 1 to 3.65 that we stored in double, or maybe that someone else stored in double and gave it to us? It might matter to your algorithm, it might not, but you should be aware whether it matters or not. Or maybe it's not 2 digits after the small dot, maybe it's more digits. And again, maybe you care, maybe you don't. So if you're a library and you're getting doubles and you don't have much choice, but if user is typing you a number directly, then you do have a choice. If you're reading JSON or XML without third-party libraries, you do have a choice to understand how many decimal digits the user entered. So it might be useful to preserve this information for the future, or it might not, or you might be better using on decimal floating point arithmetic right away. Similar thing applies to outputs. What is the expected out of your output of your program? Who will use it? Like, will it be used as an approximation? Will it be displayed to user after rounding to 2 decimal points? Can you display it to the user and round it yourself? Or should you generate a double that, when rounded to 2 decimal points, will be represented to the user correctly? The same applies when you store it for Excel, for JSON, for XML, for any format. And finally, you should understand that some things you cannot fix with enough precision. So for example, if you have square root of number, then it works. But if you're trying to evaluate the tan function, then it just jumps from positive infinity to negative infinity around some certain values. And you can calculate with 500 digits of precision, and it won't help. So actually, any kind of like discrete decision and that you take in your program with floating point numbers is potentially bad. So if you round stuff, if you make a decision with an if statement, it might be bad, it might not be. And there is a separate branch of science called numerical analysis that talks about this. So for example, if you're trying to render a progress bar, then your inputs are integers, you just want to render a progress bar, and your only requirement is that you don't show 100% unless it's fully done. Like the computation is stable, so it's fine, and you can actually do it with integers only. If you're writing a financial report that is mandated by law, then inputs are mandated by law, decimals is 2 places, outputs are mandated by law, and exact results are also mandated by law, but your algorithm is not really that stable because you have roundings all over the place, so you should be really careful with what numbers store what. If you're writing a game, you have player inputs that might be a little bit fuzzy, you render something to the display, players probably don't strive for pixel perfect, I hope, but you also have collisions, and whether player collides with a wall on this frame or on the next play may affect the game. So again, it's not really stable, so you should be careful, and you should be extra careful if you want your game saves to be transferable between different platforms, then yeah, just be careful, and even worse if your game is played over the network. If you're doing scientific calculations, hopefully you know better than me, and hopefully your inputs and outputs are integers, and hopefully you're also using numerically stable methods. So whenever possible, please use integers. It is possible in lots of cases, like there is no need to calculate polar angles to check whether two vectors are parallel, just calculate dot product. There is no need to calculate average to check that it's greater than some number, just calculate sum instead. And if you do write floating points, then please test like any other components. There is nothing intrinsically wrong with floating point numbers. They might behave a little bit weirder than usual. There are more corner cases like infinities, NaNs, and subnormals. Subnormals also warrant testing for performance, because if your program is suddenly 50 times slower, then you probably want to know that it might happen. And if you are writing some smart algorithm like Kahan summation, then test that this algorithm actually behaves better than your naive implementation. I tried it 5 times, and my first 4 attempts failed, and my Kahan algorithm implementation actually was worse, even though it's like literally 6 lines of code. I kept messing up like variable names, and I think I also messed my tests maybe like 16 times and only got it on 17th attempt. So yeah, maybe if you can, don't do it yourself. So check if there is a library that already does what you really want to do. Another idea is you can use float. If you don't really need double, you can use float, and you test how your algorithm behaves with floats. So there are only 2 to 32 of them, so you can just check all of them. And I believe this is how some hardware is actually tested. Another thought that I picked up from SecExchange is just random tests are not enough for floating points. They will find like infinities and NaNs, but they won't find corner cases that are specific for your algorithm. So yeah, you should think about corner cases for your algorithm specifically. Where do you make decisions? What happens on like edges of those decisions? Yeah, so use integers, understand your inputs and outputs, assume that everything is approximate unless you can prove otherwise, and also use better formulas before you try to increase precision, use better types, or try to implement a Kahan summation algorithm. So there are lots of ways that you can use better formulas and get much better results. So math is more powerful than programming in this case. And also, if you have to do math, then prefer to use libraries, because if you're trying to calculate Taylor series for some function manually, probably there is more efficient and numerically stable way to do it. So even if you learn something in undergraduate calculus, it doesn't mean that there isn't a better way. And if you do end up micro-optimizing and increasing precision, then be very aware that the compiler may screw you up and throw all your efforts out of the window. I also left some links here that you may find in the download presentation, and that's it for me. Thank you, and sorry for technical difficulties.